Hi, everyone. I'm Thibaut Schaeffer. Today I'm going to be talking about ZoKrates. So giving kind of a general introduction for those of you who are not familiar with the tool, and also kind of talk about some of the concepts and ideas we've been working on recently. Again, yeah, check out the episode that's going to come out soon with Zero Knowledge Podcast. That should be a good one. So before I start, I should mention ZoKrates was started at TU Berlin, and we're proud to have had the support of the Ethereum Foundation since the start. So with that out of the way, let's jump right into it. So one way we like to think about it is that in the blockchain space, since Bitcoin, we've basically seen two main trends. One trend is towards more generality with Ethereum and smart contracts, and everyone can write whatever they want, and you have all this freedom. And privacy on the other side with Zcash, with kind of more private systems. What we think at ZoKrates is that by combining those two aspects, we're likely to bring more innovation into the space and to let developers come up with the actual interesting use cases. So we really want to be up there on the right on this graph. However, if you look at Zcash, there's amazing systems being built at Zcash. However, for the average developer, it's still really, really hard to get started with zero-knowledge proofs because the abstractions are being used are very, very low level and very close to what you would be doing with an actual circuit board where actually you would want something a little bit more high level and developer friendly to get started. So we want to enable developers to write privacy preserving applications, and maybe I can kind of give a quick overview of what that could be, even though of course the use cases will be found by the developers eventually. So in general, proving facts on private data is something that you can do with those systems. In particular, proving membership in a Merkle tree, shielded token schemes, schemes such as the Zcash scheme as well, commitment schemes, and finally, maybe another type of use case that we're also looking at, which is not directly linked to privacy itself, but it's compression. So taking, for example, a number of proofs that were generated like normal using other tools, and kind of take those proofs at input and then compress them to have one single succinct proof that kind of sums up all those proofs as input. And we have some projects who are using ZoKrates to do that. For more on the applications, we have a panel this afternoon that will go more into what people are actually building with those systems. Given all those applications, the space, and especially the Ethereum community thought, oh, that would be great to be able to use those tools. However, they require some cryptographic primitives that are quite specific. And for those familiar with Ethereum, on Ethereum you can only use this EVM, the virtual machine, and actually implementing those primitives on the EVM was really, really costly in terms of gas. So last September, last year, there was a hard fork in Ethereum, which introduced basically three new primitives in the form of precompiles, what we call precompiles, which are basically primitives that you can call from the EVM, but that can be much more complex and for which you pay just a fraction of the cost because they're not executed on the virtual machine itself, but they're executed natively on the host. So you kind of have a huge savings on that. And those primitives were elliptic curve operations on altBN, which is the curve that's currently used in Zcash. So including pairing checks. And pairing checks are known for being kind of the underlying cryptographic tool necessary to use the current zero-knowledge systems, such as the one used by Zcash. So that was added into Ethereum, making it possible for anyone to go and start doing zero-knowledge proofs on Ethereum. However, that did not really happen because they were just introduced as this very, very low-level primitive, but there was no way anyone could actually take that and actually build something on top because it was so low level. You didn't even have the proving system. You just had this very kind of basic primitive. So yeah, here's some tools. Go and use them. It's actually not that easy. So that's where ZoKrates comes in. And what we actually built is a domain-specific language where you can define your computation, your privacy-preserving computation. So Ariel talked about like public inputs and private inputs. That's something you can define directly in the ZoKrates program. So here we have the main function, and the main function has inputs. The first input is private, which means that when you're going to generate proofs, this value A will not be revealed, and has also public input, so the value H will be revealed. And in this case, what we're doing in this program is proving that we know the pre-image of a given hash. So you kind of feed your secret pre-image A, and you feed the public hash H, and then you basically return 1 if the hash of A is equal to the public hash. And then you have some hash function that you can define in ZoKrates as well, and so on. So trying to have this very like high-level abstraction for people to build on. So what it looks like in general is a whole pipeline of tools. So starting from the domain-specific language, we have tools to actually run a setup phase, similar to one run in Zcash, which generates 2 different things. One thing is a prover, and the prover is basically a piece of software that will be run, let's say, on the client of the prover, or whoever wants to use the application. So in Zcash, that could be someone wanting to spend some coins. And that's something that's completely independent from any blockchain. It's just a piece of software that lets you generate proofs. And the other piece of software that we generate in the other target is a verifier, typically. And what we built is that our verifier is actually a piece of Solidity code that you can deploy directly to a blockchain, so that end-to-end you could have someone generating a proof on the client, for example, proving that they are above 18, and then sending this proof to a smart contract, and the smart contract could just take this proof and say, okay, this is valid, and do some access control based on that. So this is a kind of use case that we're looking at currently. So great, we have this tool, we have this high-level language, so we can start writing all our programs in it, and everything will be fine. So that's basically what we did. So we wrote, as seen in the previous example, we implemented a hash function, especially the SHA-256 compression function, so just 1 round of SHA-256. And here's how it went. So as you can see, our implementation has, our kind of naive implementation has 250,000 constraints. And in the case of those systems, the more constraints you have, the less efficient your system is. Because if you have a lot of constraints, it's going to take a lot of time for the prover to generate the proof, and for the setup as well to be executed. Whereas LibSNARK gadgets, which is the kind of library that most developers use currently, has an implementation of SHA-256 in just 27,000 constraints. So of course, our implementation is very naive, and we could have more optimizations. But our approach is to say, oh, we have this great implementation already. Why not just try and kind of import that into ZoKrates and see how we can kind of interoperate between those two. So our goal is going to be to find kind of a common language between those two tools, kind of ZoKrates and other tools such as LibSNARK. So we looked at what good candidates we could have for this kind of interoperability between the different tools. And you can see it as ZoKrates and the LibSNARK gadgets kind of standing on top of this common abstraction, which is basically arithmetic circuits. And arithmetic circuits can be represented in this form called R1CS, or rank 1 constraint systems, which is actually pretty simple. It's just a list of so-called constraints, and each constraint is sort of an equation like this, where you can have one multiplication, so here W times this kind of product, and so only one, let's say on the left, and no multiplication on the right, and then the elements that you multiply need to be only linear combinations, so like a sum of factors of your variables, right? So you, in terms of arithmetic circuits, you can think of it as a circuit that has plus gates and multiplication gates. And in this case, what each variable is, it's a variable that lives in a prime field, which is basically a field that has whose size is a prime, a very big prime, right? So this is a very simple abstraction, and I say, okay, let's use that. We'll just take the Let's SNARK gadget, just compile it to R1CS, take that, feed it into ZoKrates, and there we go. We have our 27,000 constraint hash function. So when we did our implementation of SHA-256, we were basically very close to R1CS, saying, okay, we create a first constraint, and we set some of the values, some of the variables to some values, and then in the next constraint, we can reuse some of the variables and say, okay, this is another constraint, and then by going through all the constraints, you can find a solution to the system, right? So just looking at R1CS, you can actually write complete programs. However, if we look at something that we would want to do, which is turning a number into its bit representation, and that's something that's really useful, especially in the case of SHA-256, because SHA-256 is based on bits. So you absolutely need to have a way to kind of represent bits to implement this algorithm. And it turns out that if you want to take a number, which is living in this kind of prime field, so it's just like an integer, and you want from that to output the bits that represent this number, and imagine you only have this abstraction that we had before, which is just a bunch of constraints that are just multiplication and additions. Actually, it's going to be really, really hard if you just have those tools to go from a number to its bit representation. But here we can see what's actually being used in those systems in order to have efficient circuits, and it's the following. It's to say, instead of executing the kind of bit decomposition in the circuit, I'm going to have this first line with the kind of the hashtag there, where I just set two new variables, C1 and C2, to being the result, right? So it's really easy, like off the circuit, to find a bit representation of a number. And then this is not enough, right? If I just come up with two values, then I could come up with anything, and then I could even put like 5 and 4, which wouldn't make sense. So then the important thing is to then, once I have the result of the computation, I need to have a bunch of constraints that make sure that this result is actually correct. So in this case, if I come up with C1 and C2, which are the bit representation of C, then I need to check 3 things. I need to check that C is actually equal to C1 times 1 plus C2 times 2, right? And that's actually just one constraint. It kind of it works in our current abstraction of just being one constraint to the system. And then I also need to check that C1 and C2 are actually either 0 or 1, right? Because I want to make sure that those are actually bits. So to do that, we use a trick where you just make sure that the square of the number is equal to the number. Because 0 times 0 is 0, 1 times 1 is 1, and there's no other number that satisfies this equation in a prime field. So the kind of general idea is to say, okay, we have this computation, but actually a lot of the times it's way more efficient to do the computation of the circuit and then just verify the computation in the circuit. And that's what we're doing here, where we can do bit decomposition into 3 constraints. And if you have more bits, it actually scales linearly, right? So this is something that was not captured in the R1CS. R1CS just told you that those are the lines, so those are pretty much what R1CS is, but R1CS doesn't give you this, kind of the way to solve the system. And that's something that we also need to carry if we want to interoperate between different systems, right? So from that, we came up with this very simple abstraction where you have basically just two things in circuits. One thing is assertions, and assertions, you can think of them as being the exact same thing as R1CS. It's just a bunch of constraints, a bunch of equations that need to hold. And you have solvers, which are ways for someone running the program to find actually which values to set to the variables before they can check the constraints. And those two things are necessary so that we can kind of take advantage of all the power of the SHA-256 libsnark implementation. So we kind of took that approach and applied it to SHA-256, and this is what we ended up with. We have basically a ZoKrates function, which is a wrapper around the SHA-256 libsnark. So the way it works is that SHA-256 in our case takes 512 inputs. I have one too many here. So it takes your inputs, and then you have this solver. So nothing happens on the circuit itself, but the solver just takes the whole constraint system for SHA-256 in libsnark and just sets every single variable of the system to what it should be, right? So based on your inputs, it sets all the variables, like all the intermediate variables. There's actually like 27,000 variables. It sets them to some values. And then that's something that's executed in libsnark. So from ZoKrates, we actually do a call to libsnark to say, hey, what's the solution to this big constraint system for those inputs? And libsnark is going to give us an answer. Okay, those are all the values you need to have. But then, again, that's not enough. So we need to add all the constraints. And again, those constraints, we can get them from libsnark because libsnark has the whole circuit. And then we can just verify those constraints. And in the end, we just return whatever subset of all the intermediate variables is our actual output. In this case, the 256 bits. So we have this in ZoKrates, and that's kind of first step that we took in this direction. But we actually want to go further to actually have a real way for systems to interoperate. And for the R1CS part, for the constraints part, this is actually really easy because it's just a bunch of constraints. But in this case, when we did our SHA-256 integration, we were still calling from ZoKrates to libsnark to get the witness, to get the solution to the system. And it would be actually great if you could actually get the solution to a system without having libsnark at all. So the idea would be to instead export from libsnark the witness generation, this kind of solver bit, and kind of have that alongside the constraint system so that you could directly import and have the witness generation included. So what we experimented with, so of course the libsnark solvers, which I described earlier. Inside ZoKrates, we also have solvers that are being used inside the language in some cases to kind of resolve the constraint system, and they're written in Rust. And one idea we have is to use WebAssembly in order for all the different tools to compile their solvers, so that then you just need to have a WebAssembly runtime so that you can run the solvers for your system. And that doesn't have any security implications because the whole security of your system relies on the constraints and not on the witness generation. So having something that's really, really portable here makes sense to us. So that's something we're looking at as well. So in terms of the kind of next steps that we're looking at, so having more stuff on interoperability, making it easier for those systems to interoperate, so that we don't have to re-implement SHA in every single toolbox, but instead we can share those implementations. We're also working on a type system. So we have two main reasons why we're working on type systems. So in the current version of ZoKrates, there's only one type, which is the field elements. But this can be very cumbersome for developers to work with, especially if you're talking about a hash function, then you have like 256 outputs. That's not really easy to work with. So the first kind of type that we would want to have is kind of static arrays, so that you can actually in ZoKrates have this array which represent a number of values, and then this gets compiled down to the actual field elements. And there's a second use case where the type system is going to be really interesting is for safety itself. So when you're talking about bits, you always need to make sure that whatever variable represent a bit, so in this case, the C1 and the C2 here, all of this only makes sense if C1 and C2 are 0 or 1. And that's something that we're looking at enforcing in the type system itself, so that if in ZoKrates you allocate a bit, then it's going to automatically make sure that this bit is always 0, 1 all the way through in your program. Finally, integrating with other backends is something we're looking at. So currently we target Ethereum with a specific proof system and a specific curve, but there is no reason why we couldn't just take ZoKrates and target a different curve or a different proof system as long as it's based on the R1CS abstraction. Then just a quick wish list for the ecosystem at large, because we start having people working on those tools and some stuff that we think could be interesting for space. So first, there's this tool called Bellman, which is the library developed by Zcash, which does both kind of circuit generation and also proving. And that's something that is really interesting for us for many reasons. One of them being that it's based on Rust, and we're also building on Rust. Another thing is that they use the concept of streaming the constraints, so that you have actually reduced memory usage compared to other proving tools. The drawback of Bellman is that it is developed inside Zcash, so it's very focused on the Zcash use cases. So it only supports one curve, it only supports one proof system. So if we can have Bellman as a kind of community tool that people build on and add more proof systems and more curves, there's already some people interested in adding the Albion curve to Bellman, which would be awesome as well. Then in terms of the curves themselves, embracing BLS 12381 could be super interesting as well. That's something we're also looking at, but in terms of the support currently, it's pretty restricted to the kind of Zcash community, so it would be great to have more implementation of BLS 12381, and that's something that the Ethereum Foundation is also interested in. So if you're interested in porting BLS 12381 to a different language, just reach out. I can help on that. Also, having more developers, because there's so much stuff to do. Like, it's pretty much kind of open territory now. So we have interesting topics if you want to work on those things, and yeah, there's just so much stuff to do. And finally, sharing, I think, is something that's really important, because right now the community kind of benefits of all the great work that the LibSNARK people have been doing and the Zcash people have been doing on Bellman. But we could use more sharing, like events like today, or the kind of ZCon conference in Montreal, also meetups. So I'm also looking at ways that people can connect more and share their experience with the system, so that we can build best practices and have actual use cases out there. So that's all for me. You can join this afternoon. We have a panel on the use cases themselves, and also definitely check out the tool and come talk to me if you have any kind of disagreement on anything I said. I'm definitely interested to hear your perspective. Thank you.
So I think if there's any questions, I'm going to be running around with the mic. Cool.
Thanks for a great talk. So 2 questions. First, you mentioned the SHA-256. So it's ready now, it can be used. Right?
Yeah, we have 2 implementations. One is ZoKrates native implementation, which is not efficient. And we have a integration with LibSNARK that you can use. I can kind of show you how to use it. It's not on master yet, but it's available already.
Cool. And second question is, you mentioned the types, which can be Boolean in the future, but now currently you only support the fields. So the operators are also just arithmetic circuits. So I don't have logical operators. Is that correct? So I have to implement logical operators myself with the arithmetical stuff.
At the moment, it's the case, but once we have types, you would definitely have XOR and all those operators.
So can you estimate the ETA for this?
That's something we're working on now. We want to be sure we get it right, but it should be this year.
Okay, thanks.
Okay, all the way back.
Thank you. So my question is on the trusted setup. You said you can make the trusted setup in ZoKrates, but if I set up the trusted setup, it's not really trusted. So could you use the Zcash trusted setup for the SHA example?
So that's something that would be really interesting to do. That's something we don't have at the moment. We only have the centralized setup. There are some use cases which work with a centralized setup, especially if you're doing the setup and you're the verifier. So in some cases, it's okay to have this trusted setup. But if you're interested to work on having a more decentralized setup in ZoKrates, that's definitely something we would support. And yeah, definitely.
Any other questions?
Hi, thanks for the talk. Do you have any ideas for ETH Berlin projects, like hackathon-size projects that we could attempt to do with ZoKrates?
Sure. There is one proposal for a project which is more about ZoKrates itself to integrate ZoKrates with Remix. So that's more on the kind of developer tool side of things. In terms of kind of toy project that you could use, that you could do during a hackathon, yeah, I think you could already use kind of see what you can do with hash functions in general. I know there's some people from Gnosis in the room that also have some very interesting ideas. So maybe kind of connect with them. And also this afternoon we're going to have this panel, so maybe we'll have some ideas after that. Cool.
Hi, thanks for the talk. In the context of verifying Merkle proofs, what needs to be added on ZoKrates to be able to do the verification efficiently? And ideally, if we could do the proof generation for multiple proofs in one, like a recursive setup thing?
Do you mean recursive SNARKs?
I have heard of the name, but I'm not sure if that's what you would want. Ideally, a way to make multiple Merkle proofs of inclusion in one proof.
Okay, I don't see anything that would prevent you from doing that based on a hash function. So you could take a hash function in ZoKrates and then implement a Merkle tree on top of that, and then use that. So I think you could do it today, and we have people who did similar stuff.
Okay.
If there aren't any more questions, we can take okay, we'll give you one more, but then we can take a little break before Howard Wu comes up and talks about the Zik.
So in EVM, there is a precompiled contract with this trusted setup based on Zcash trusted setup. Is that correct?
So your trusted setup is not based on the curve, it's based on the circuit. And in this case, each developer comes up with the circuit. So typically, you would do the trusted setup. So whoever sets up the kind of verifier does the trusted setup.
But what about the EVM precompiled contract?
Oh, the precompiled contract is only for the pairing checks.
Okay.
And the pairing checks are used in the process of verifying a proof. But they don't have any trusted setup. It's just,
okay.
It's just EC cryptography.
Okay,
yeah.
Thanks.
Cool, cool. Thanks a lot.
Thank you.
So